Good morning to my dear students. In the last class, we have started the topic magnetostatics. What is the magnetostatics? It is the study of the magnets or magnetic materials which are at rest. This is the magnetostatics. In this magnetostatics, what are the basic points? Is it those required for the study of the next points? All those points we have discussed in the last class. That is, if I highlight all those points, then the magnetic effect of electric current means whenever the current flows through a conductor, the magnetic field is produced around the conductor, isn't it? Therefore, the magnetic field, it is a vector, that is, which has the magnitude as well as the direction. Now, if it has got the magnitude and direction means, then how to determine the direction, is it, and how to determine the magnitude? Then all those points we have discussed in the last class, and in addition to this one, then what is the formula of the magnetic field due to a straight conductor, what is the formula of the magnetic field on the axis of a circular conductor, and the field at any point on the axis of solenoid. All these points already which you have studied in your lower classes, all those points again they have revised so that you can understand the next two points. Now, today we are going to discuss the point regarding the Helmholtz Galvanometer. Now here, this Helmholtz Galvanometer, it is a modified form of the tangent galvanometer. Now, what is the tangent galvanometer? That already we have studied in your lower classes. This point also. Then, if I recall the point, tangent galvanometer is what? It is an instrument, isn't it, which is used for the determination of the current in the circuit. Now here, for the determination of the current in the circuit, we are having the different instruments like the galvanometer is there for the detection of the current, and how much amount of current is there for the determination of that. We are having the instruments like ammeter, isn't it? And here, Helmholtz galvanometer, it is also, or galvanometer, it is also an instrument which is used for the determination of the current. Then, what is the tangent galvanometer? Its theory, construction, already we have studied in your lower classes. Now, let us come to the next one, that is the Helmholtz galvanometer. Now, here, this Helmholtz galvanometer, it is a modified form of the tangent galvanometer. Now, the modified form of the tangent galvanometer is known as the Helmholtz galvanometer. Well, in case of the tangent galvanometer, there are some the drawbacks are there. Then what are the drawbacks? Means whatever the current we measuring by using the tangent galvanometer, that tangent galvanometer, that value of the current, it is what it is the not correct one, isn't it? Then why it is not correct? The reason is that this tangent galvanometer, it works on the principle of what? It works on the principle of the tangent law. Now, what is the tangent law? Tangent law, B is equal to BH tan theta. This one. This is called as a tangent. Now, tangent galvanometer works on the principle of the tangent law. Now, what is this B? B is the magnetic field produced due to the flow of the current. And BH is what? It is the Earth's magnetic field. And next, what is the theta? It is the angle between B and BH. Suppose this is the B and this is the BH, then this is what is the theta. Now, from this figure you can understand that here, when you take the tan theta, then what you get here? Tan theta is the from this one, which is equal to opposite divided by adjacent. Now, this opposite, it is nothing but it is equal to B, isn't it? And adjacent value is what? It is the BH. Now, when you cross multiply here, then you will get B is equal to BH tan theta, isn't it? Therefore, the tangent galvanometer works on the principle of the tangent law. As I made it clear that B is what? It is a magnetic field produced due to the flow of the current, and BH is the Earth's magnetic field. Theta is angle between B and BH. This one. Second thing is that the important point, whatever the values of B and BH are there, then these two values must be uniform, isn't it? They must be uniform. And the next is, they should be perpendicular to each other, isn't it? Whenever this condition is satisfied, then the tangent law, it is holds good, And if the tangent law is forceful, then on the basis of this tangent law, whatever the instruments are working, by using those instruments, then whatever the current we calculate, that will be found to be correct. Here, practically what will happen is, in case of the tangent galvanometer, the value of V and VH, they should be remains uniform, isn't it? But in the case of the tangent galvanometer, it is found that the value of V, isn't it, means it is a field produced due to the flow of current. It is not uniform, isn't it? Now, see, if it is not uniform, means then this what is the V and VH are not uniform, means then this tangent law will not be holds good. If it is not holds good, means by using this what is the law, then whatever the instrument is working, that is the tangent galvanometer, that is also be not giving the correct value. That is the drawback of the tangent galvanometer. I think this point also already you have studied in your lower classes, but you might have forgotten it, so that again I have revised it. Isn't it? That means by using the tangent galvanometer, whatever the current we measure, that is what is not found to be correct. That what is the reason? The reason is that this tangent galvanometer works on the principle of tangent law, that is V. What is the V? V is equal to VH tan theta. What is this V? V is the magnetic field due to the flow of current, Earth's magnetic field. Theta is angle between V and VH. Isn't it? And next here, this what is the, in case of the tangent galvanometer, what is happening is the value of V, that means field due to the flow of current, it is not found to be uniform. If it is not uniform, then this law is not holds good. Hence, the instrument which is working on the principle, it is not correct. So that by using the tangent galvanometer, whatever the value of the current we measure, it is not found to be correct. So that drawback was what it is the overcome by using this what is the Helmholtz galvanometer. Now let us see here. Then the principle is same. Isn't it? This Helmholtz galvanometer, it is also works on the principle of tangent law, that is V is equal to VH tan theta. Isn't it? This one. And in this Helmholtz galvanometer, it is found that V is it and VH, these two are what is the uniform, isn't it? Hence, the tangent law is holds good. As a result of which, whatever the instrument working on this principle, that gives the correct value, isn't it? Therefore, in this Helmholtz galvanometer works on the principle of the tangent law. Then what is the tangent law? V is equal to VH tan theta. Once again, I repeat here. What is this V? It is the field due to the flow of current, Earth's magnetic field, and theta, it is also be known to you. Now let us try to understand about the construction of this Helmholtz galvanometer. Now here, in the tangent galvanometer has one circular what is the coil. Then instead of using one circular coil, in case of the Helmholtz galvanometer, the two circular coils are used. Now here, this is the instrument, isn't it? Which is the Helmholtz galvanometer. Then you are observing that in this one there are two what is the circular, what is the coils, isn't it? Which are what is placed on a horizontal place, such that the planes of the two coils are parallel to each other. That means the plane of is this coil and the plane of this coil, these two are what is a parallel, and the distance between the two what is the coils, it is equal to the radius of one of the coil. Then here one more point is, whatever the two coils you are using here, these two coils must be identical, isn't it? Then identical means both must be one another same. One is same with respect to what? The radius of both the coils is same, and the number of turns in both the coils are also be same, isn't it? Therefore, this Helmholtz galvanometer consists of two identical coils which are placed on a horizontal frame, so that the planes of the two circular coils are parallel to each other, and the distance between the two coils, it is equal to the radius of what is the one of the coil, isn't it? That means the distance between these two, it is equal to radius of this coil or radius of this coil, because these two are identical. The next one more thing is that the two coils are connected in series, isn't it? The two coils are connected in series. Then since these two are in series, the amount of current flowing through these two coils is also the same, because in lower classes you have studied that in series combination current remains the same. Are you following? Therefore, since these two coils are in series, so that the amount of current flowing through both the coils is same, and that will be in the same direction also, isn't it? They are in the same direction. When in series combination, the current and its direction is also be what it is the same, isn't it? Now, here you have studied that in lower classes. If let us consider the two resistors, isn't it, R1 and R2, when they are said to be connected in series, then that they are said to be connected in series when they are connected end to end like this. Now, in series combination, what will happen is the current remains the same, isn't it? Current remains the same both in magnitude as well as in direction, isn't it? Then magnitude means if the 2 amperes here, this also be here also be 2 amperes, and the direction is also be same, isn't it? Therefore, since the direction of the amount of current and the magnitude and direction of the current in both the coils, it is what is the same, so that what will happen is the magnetic field at any point, isn't it? The magnetic field at any point is also be a field which the two coils must be in will be in the same direction, isn't it? Why the direction of magnetic field due to the two coils is in the same direction? Because the direction of the current is same, isn't it? Suppose when you consider in both the coils the direction of the current is clockwise, isn't it? Then direction of the current in this is clockwise, here also be in the clockwise, so that the direction of the magnetic field at any point due to the two coils is also be in the same direction, isn't it? This one. Now this is about what is the construction of what is the Helmholtz Galvanometer. Once again I repeat here, the Helmholtz Galvanometer, what is the consists of the two identical circular coils, the placed or mounted on a horizontal base, so that the planes of the two circular coils are parallel and both are connected in series. Since the two coils are connected in series, hence the magnitude and direction of the current in both the coils it is same. And since the magnitude and direction of the current is the same in both the coils, hence the magnetic field at any point is also be in the same direction. The field due to both the coils is also be in the same direction. This is what is the construction of the Helmholtz Galvanometer. Now, first we have discussed what is the principle, isn't it? Now, this Helmholtz Galvanometer works on the principle of the tangent law. Then, what is the tangent law? B is equal to BH tan theta. Then B is the magnetic field due to the flow of current, and this BH is the Earth's magnetic field, and theta which is also known to you. And the next, this point also I made it clear that when this tangent law is forceful, this tangent law is forceful only when this both B and BH must be uniform and they must be perpendicular to each other. This is the principle. And the second, already I have explained you regarding the construction of this what is the Helmholtz Galvanometer. Now, after understanding this principle and the construction of the Helmholtz Galvanometer, now let us come to the theory of the Helmholtz Galvanometer. Yes. Now, we have discussed regarding the principle and construction of the Helmholtz Galvanometer. Now, let us try to understand the theory of the Helmholtz Galvanometer. Now, you are going to familiar that this Helmholtz Galvanometer consists of the two identical circular coils which are mounted on a horizontal base, so that their planes are parallel to each other and they are connected in series, isn't it? Since they are connected in series, therefore the direction of the magnitude and direction of the current in both the coils it is what it is the same, isn't it? Now here in the figure, let us consider this is one coil, this is another coil, the two identical coils, isn't it? Separated by a distance equal to the radius of the one of the coil already I told you. That means from here to here, it is the radius, and this is the midpoint means now this distance will become equal to r by 2, and this is also equal to r by 2. Now the total distance between the two, what is the centers of the coil, which is equal to the radius. Now what will happen is one interesting thing, that is in this Helmholtz Galvanometer, how the field due to the flow of current remains uniform. Let us try to understand here. Now, yes, you know that since these two are connected in series, hence the magnetic field at any point due to the two coils is in the same direction, isn't it? Next, here at any point you take, there are two magnetic fields are active at any point, isn't it? On the axis of these two water coils, you take it. At that point there are two magnetic fields, isn't it? One due to the first coil C1, another is due to the second coil, isn't it? Now, according to the White-Sauer's law, as you know that the magnetic field, it is inversely proportional to the distance, isn't it? Means inversely proportional means what? If the distance is less, magnetic field will be more, isn't it? Now, let us consider at this point, isn't it? At the center of the first coil, field due to the C1 is more, whereas field due to the C2 is less, isn't it? Because this is nearer to this one, therefore what is the field due to the C1 at this point it is more, whereas field due to this here it is less, isn't it? Now, as you move from C1 to C2, carefully observe the figure. As you move from C1 to C2, as you move from C1 to C2 means what? The point from C1 is increasing and moving towards C2 means the distance of the point from C2 decreasing. Therefore, here as we move from C1 to C2, field due to C1 decreases, whereas field due to C2 increases. But the total value remains the same. How means? Let us take an example, isn't it? Now at this point, carefully you observe here. Field due to the C1 is what it is the 8 Tesla, and field due to C2 is what is the 2 Tesla. That will be equal to how much it is the 10. Are you following? Next, when you come here, isn't it? You are moving away means distance increases means field due to C1 decreases, whereas it has come nearer to C2 means what? Field due to C2 increases, isn't it? Therefore, here at this point, field due to C1 decreases, field due to C2 increases. Means field due to the C1 here, if you take this as 7 decreases, but here it is increases 3, again it will be equal to 10. Are you following? Next, similarly when you point this here, then let us say it is a 6 and here it is increases 4, that is equal to 10. At the midpoint, isn't it? Field due to the C1 and field due to the C2, it is equal. That is 5 plus 5, which is equal to 10. Next, when you move away from it, then what will happen is field due to this, that is 5 plus 5, that is equal to 10 here. And when you come here, then field due to this C1 is 4, whereas field due to C2 is equal to 6, like this. Then it goes on like this way. Therefore, what will happen is, as we move from what is C1 to C2, as we move from C1 to C2, the field due to C1 decreases, field due to the C2, what it is the increases. That means we use the word like this, carefully. The rate at which, is it, field due to C1 decreases, at the same rate field due to C2 increases. That means here you can see that what it is, it has reduced from 8 to 7 means by how much? 1. Then here it is increased by 1. Isn't it? That is rate of decrease of the field due to C1, 1, is equal to rate of increase of C2, that is 2 to 3. Same again, 7 to 1, how much it increased to 1? And here 3 to 4 increases. That is the rate of decrease of the magnetic field due to C1 is equal to the rate of increase of the magnetic field due to C2. Is it? That rate will be remains the same. Then only what will happen is the field will remain uniform, that is constant. Therefore, that rate of change, that is increase or decrease, both we call it as a change. That is Once again, I repeat the sentence here. The rate of increase of the magnetic field due to C1 is equal to rate of increase of the magnetic field due to C. That is what, once again, the rate of decrease of magnetic field due to C1 is equal to the rate of increase of magnetic field due to the C. Both are same. Generally, what will happen is the magnetic field will be remains constant. That rate of increase or decrease, generally we use the word that is the rate of change of magnetic field should be remains the same, that is the remains constant. This is the what condition for the uniform of the magnetic field. Then that is what we are doing. That is this dB by dx. It represents what? The rate of change of magnetic field that should be remains the same, that is a constant. Isn't it? Then if this is a constant means when you take its differentiation, the differentiation of a constant will become equal to 0. Isn't it? Therefore, d square b divided by dx square is equal to 0. Now, as you know that field at any point on the axis of the circular coil formula, it is what is this one? Isn't it? That is b is equal to mu naught by 4 pi 2 pi n I r square divided by r square plus x square whole raised to 3 by 2. Then what is this x? It is the distance of the point from the center, this one. Then when it is here, this one, like this one. Now, this complete constant factors to take out here, mu naught divided by 4 pi is a constant, 2 pi n I r square. Isn't it? This complete factor is a constant. Then here you see number of terms, both in the cases it is what is the same because they are identical. Then radius is also the same. Then the same amount of current is flowing. So that this complete factor is a constant that I have taken out. Then this is this one. Now this complete, it is a constant that is represented by k. Now this, what is the denominator value take to the numerator, it will become as a power minus. Isn't it? Now this is the value of b. Therefore, the next dv by dx is equal to differentiate this one. Isn't it? Now what will happen is k is a constant. Isn't it? Then according to the differentiation, then what is the d by dx or this is equal to, isn't it? d by dx of x raised to n. General formula is what? It is equal to n into x to the power of n minus 1. This is what we are using here. Isn't it? This k is a constant, then this is n, and differentiation of this, when you take it, then the power decreases by 1. That is, earlier it is minus 3 by 2. When its power decreases by 1, it will become as minus 5 by 2. And the next is differentiation of the internal, what is the function, that is, what is the differentiation of this x square is 2x because r is a constant. Now this is the d by dx. Now when you, what is the rearrange in terms, then this 2 and this 2, it will get cancelled. Therefore, you will get it here, this one, then this and this one. Then again, you take its second differentiation. Isn't it? d square b divided by dx square is equal to, this is a constant. Isn't it? Now, this factor differentiation by product we are using, then keep this as a constant, differentiation of this is 1. Isn't it? Plus, now this you keep it as a constant, differentiation of this, it is equal to n into, that is this is put to constant, then n into what it is the x to the power n minus 1 means when you decrease its power by 1, then you will get minus 7 by 2, and differentiation of this internal function is 1 to the 2x. This is what you get it here. Next, this is remains the same. Isn't it? Next, what will happen is, since it is minus here, that will get it, then x by 2. This is same. Isn't it? And 2x. And here, what will happen is this 2 and this 2, it will get cancelled. Isn't it? Then, for uniform, what is the magnetic field? Then this d square b divided by dx square must be equal to 0. Isn't it? This is what we have shown it here. Now, when you equate this factor to be 0, isn't it? Then this is what you get it here, this one, and this is cancelled, minus 5x square you get, isn't it? This is equal to 0, isn't it? And now, when you simplify this one, then you see here what you get it. Now here, what will happen is this is equal to 0 means this one, the bracket quantity must be equal to 0 because this is a constant. Therefore, it is r square plus x square raised to minus 5 by 2. Is it minus 5x square in r square plus x square raised to minus 7 by 2. This is equal to 0. Isn't it? This is what we get here. And here what we get is this 5x square into r square plus x square raised to minus 5 by minus 7 by 2. It is equal to this is equal to then r square plus x square raised to minus 5 by 2. Therefore, r 5x square it is equal to, now this factor comes to denominator, that is r square plus x square raised to minus 5 by 2 divided by r square plus x square raised to minus 7 by 2. Now here, when this factor goes to the numerator, base is the same, power will be added, then you will get plus 7 by 2 minus 5 by 2 is 1 it is. Therefore, this you will get it here as the 5x square is equal to r square plus x square. This is what it is. Are you following? That is, base, when you take to the numerator, base is same, power will be added, then this will become as a plus. Isn't it? Plus 7 by 2 minus 7 by 2 means 2 by 2 you will get, that is 1. Then it is equal to this one. Now what you do is this x square take to the left side, then what you get here, the directly 4x square is equal to r square, then x square which is equal to r square divided by what becomes 4. Isn't it? Now this here you can see that x is equal to, when you take the square root of this one, then square root of r square is r and square root of 4 is what, 2. Therefore you get it here plus r minus of r divided by 2. Isn't it? Therefore, this is what the condition for the uniform magnetic field. That is, x should be equal to how much it is, plus or minus of r by 2. This is the condition for uniform of the magnetic field. Then, when the magnetic field is uniform, then I have told you that the tangent law is holds good, isn't it? Then the instrument it is working what it is properly. Hence, whatever the current is it we calculate by using this instrument, it is found to be the correct one. This is the condition for what is the uniform of the magnetic field. X is equal to plus or minus of r2. Isn't it? That is the distance it is equal to. Distance means what here? The this what is the distance of the point from the what it is the center of the edge of the point, which is equal to r by 2. Isn't it? That means, yes, I have shown you, is it already in the figure. If I draw that one, you can see that here this. Now see, this is the point at the center, then this is equal to r by 2 and this is also equal to r by 2. Then distance of the point from the center of the first one, that is x. Either this value or this value, which is equal to r by 2. Isn't it? Now, this distance is r by 2, this distance is r by 2 means, now this total distance r by 2 plus r by 2 will be equal to how much it is r. That means, the distance between the two centers of the coil, it is equal to radius of the one of the coil. Isn't it? Then, when you maintain that distance between the two coils or distance between the centers of the two coils is equal to the radius, then the magnetic field will be the uniform. Isn't it? Then don't confuse that. Then x is equal to r by 2 means here this distance is r by 2. X distance of the point from the center of the coil. Isn't it? X is 2. Then this is r by 2. This also be r by 2 means then total distance will be equal to how much it is r. Isn't it? Then this is the condition for uniform of the magnetic field. Isn't it? Now the next we are having one more what is the derivation, that is, then as you know that Helmholtz Galvanometer it is used for the measurement of the current means, then for the calculation of the current we need a formula. Isn't it? For the calculation of the current, let us see what is the formula of the current for current through the Helmholtz Galvanometer that we are going to derive. Yes. Now, as you know that Helmholtz Galvanometer it is an instrument used for the measurement of current. Therefore, for the calculation of the current, we need a formula for that. Now let us derive the formula of the current flowing for the calculation of the current flowing through the Helmholtz galvanometer. We asked to know that when you consider this is the point P, isn't it? Then field at the point P, since this is the midpoint, isn't it? Therefore, field at this point it is equal to field due to the C1 and field due to the C2. Both are in the same direction, isn't it? Now, since they are in the same direction and that will be equal also. Why it is to be equal? Because since the 2 points are connected in series, means since they are in series, hence the magnitude and direction of the current is same. Same magnitude, same value. When the current is same, magnetic field is same, and in the same direction means the magnetic field is also be what it is in the same direction. If you consider that due to the C1 magnetic field is what it is V1 and this is V2, then both are in the same direction. If the two vectors are in the same direction, then you know that the resultant vector is equal to sum of these two, is V1 plus V2, and they are equal also. Therefore, then whatever the V1 value is there, then V2 is also the same. Hence, the total value is equal to field of the first plus field of the second. 2 times it is. Therefore, that is what we are done. Therefore, field at this, what is the field at P? At P is what B is equal to 2 times field due to the each point, isn't it? Now, the general formula of the field at any point on the axis of a circular coil is what it is this one, the 2 I have written. Then this field at any point is it on the axis of a circular coil is mu naught by 2 pi n I r square divided by r square plus x square raised to 3 by 2. Where x is what? Distance of the point from the center. Either you take from here or you take from here. Both is equal to what is the x value is r by 2. Now that value is it you substitute here, everything is same, is it? Then instead of x I will substitute as r by 2. When you take the square of this one, then you will get r square plus x square, that is 3 by 2 as it is. Isn't it? Now, you come here, when you simplify this one, then what you get it here? 2 into that is a 4 pi, you will get it here. Then mu naught by 4 pi, is it as it is? And when you multiply with this, what is the 2? Then you will get it here 4 pi n I r square divided by, then this is it r, when you take LCM, then 4 r square plus r square is 5 r square raised to 3 by 2. Then this 4 pi and this 4 pi will get cancelled. Then here you will get in the numerator this is it cancel. Then mu naught is it n I r square as it is. Now since this what 3 by 2 is for this complete factor, therefore first what it is, take the 5 raised to 3 by 2 I have written it. When you take the it's as a 3 by 2 is 2 will get cancelled, r2 we get, then divided by for this also. Now 4 can be written as 2 square, isn't it? Now this 4 can be written as 2 square raised to 3 by 2 means 2 will get cancelled, you will get 2 cube, that 2 cube is nothing but it is equal to 8, isn't it? Now what you do is here, this what 8 it goes to the numerator, then you will get it here 8 mu naught n I is it r square divided by r raised to 3 by 2 means 5 root 5, isn't it, r cube. Then what will happen is 1 this r square and r2 means 1 gets cancelled, you left with 1 r, remaining is as it is. Now see, this is the net magnetic field at this point due to both the coils. Then you also know that this Helmholtz galvanometer, it works on the principle of the tangent law, isn't it? What is the formula of the tangent law? That is V is equal to BH tan theta. You also are very familiar that V is nothing but it is the field due to the flow of current, isn't it? Now we have calculated that field at this point due to the flow of current value, it is equal to this much, that I have written it, and that BH tan theta as it is. Now see, from this is it expression, we want to get the formula of the current, so that from this is it that I is equal to remaining all the factors to take to the right side, then you cross multiply here 5 with 5 r BH divided this will comes to the denominator. Now this is the value of I. Then when you look at this formula, you can see that isn't it, this complete factor it is a constant, isn't it? 5 root 5 r radius of the coil for a given Helmholtz galvanometer, it is a constant, and Earth's magnetic field at a particular place Earth's magnetic field, it is also be a constant, isn't it? Then in the lower classes you have studied that Earth's magnetic field at a particular place, it is a constant only at a particular place, isn't it? When you change the place, then the H value it is different. But at whatever the place here you are going to measure the current, at that what is the place, VH is a constant. Therefore, this is a constant and you not absolute parameter, that is a constant. N is nothing but what? How many number of turns are present, isn't it, on the coil, that is also a constant, isn't it? Now this complete, it is a constant that we written as a K. Therefore, I is equal to this complete, it is a constant that they are written as K into tan theta, where K is equal to this much. Remember that the K, which is a constant, that constant it is known as what is reduction factor of the Helmholtz galvanometer. What it is? It is a constant called reduction factor of Helmholtz galvanometer. Now, by using this formula, we can calculate the amount of current flowing through the Helmholtz galvanometer. Now, see, this is what the complete, the principle, construction and working of the Helmholtz galvanometer, and by using this Helmholtz galvanometer, how to calibrate the current, the constant formula is one, isn't it? Now, just I will highlight this point. Yeah, from the beginning, yes, you know that Helmholtz galvanometer, it is the what is the instrument which is used for the measurement of the current. It is the what is the revised or modified form of the tangent galvanometer is called as the Helmholtz galvanometer, isn't it? There is some drawback it is there in the tangent galvanometer. What is the drawback? All those things I have meant. What is the made it clear? Then to overcome what it is that drawback, this what is the device it is what it is developed, that is the Helmholtz galvanometer. Now I think this is the complete principle, construction, working and the theory of the Helmholtz galvanometer. Now I will stop here. The remaining points we will discuss in the next.